I welcome you all to the session of engine system and performance, and today we shall discuss about CI engine performance and identify a few factors those affect CI engine performance. In our last two classes we have discussed about SI engine performance, representing performance curves and then performance map. Now, if we talk about CI engine performance, essentially the parameters used to specify or indicate engine performance are same, like indicated horsepower, brake horsepower, then mechanical efficiency, indicated thermal efficiency. And as you had discussed, if we need to compare the performance of two dissimilar engines, certainly there are some specific parameters which are used to represent based on the data set, and those are BSFC, that is brake specific fuel consumption, brake mean effective pressure, and engine mean speed. So, now if we recall all those performance curves, those curves will be qualitatively similar even for the CI engines. Why I am telling qualitatively? Because certainly if we measure engine performance in terms of efficiency or indicated horsepower, brake horsepower, those are used to measure indicated thermal efficiency and brake thermal efficiency. Quantitatively efficiency will be higher for the CI engines, because we all know compression ratio is higher for CI engines. So, what we can say that engine performance curves, those we have discussed in the context of SI engines, those curves will be similar to measure or to identify or to indicate the performance of CI engines as well, but we can say qualitatively. Quantitatively, certainly these curves will be little different than what we had seen earlier in the context of SI engines. Now, you all have studied in your undergraduate internal combustion engine course that to establish some efficiencies like indicated thermal efficiency, then mechanical efficiency, and most importantly volumetric efficiency, all these efficiencies are established mathematical form, to be precise, by comparing the processes those are there in real engine with air standard cycles. And you have studied that there are some variations between air standard cycle and the cycles used for SI and CI engines, and certainly some differences you have studied by this time. Those are essentially consideration of constant specific heat during the cycle, then assuming cycle to be an thermodynamic cycle, and most importantly that assuming air to be an ideal gas. But there are some common factors for both the CI and SI engines if we would like to compare actual or real cycle and the air standard cycle. But in addition to these common factors, there are some unique features which are special to the operation of CI engines. So, we shall discuss those special features, and those features or factors really are very important for the performance of CI engines. But before we go to discuss about those unique features, let us briefly recapitulate our understanding on this particular aspect, that is the basic difference between air standard cycle and real cycles. So, if we write these common factors for both SI and CI engines. These factors are common. So, essentially you are trying to recapitulate the difference between air cycle and real engine cycle. Let us quickly discuss all these. So, first one is certainly that is cycle or cycles, those used to compare the processes of a CI engine or of a SI engine. These cycles are not the thermodynamic cycles, rather these cycles are called as mechanical cycles, because a cycle is said to be a thermodynamic cycle if the composition and mass of the working substance will not be changed at the end of the cycle. What we can understand from the cycle or real cycle of any engine, we see that essentially air is drawn into the engine cylinder during intake stroke, or sometimes it is 90% air or 10% depending upon the requirement, that is charge. Air fuel mixture is introduced into the engine cylinder during intake stroke, while at the end of the cycle, that is during or at the end of exhaust stroke, we get some combustion products. So, compositions are not same and mass is also not same for the working substance. So, this is essentially mechanical cycle, not the thermodynamic cycle. Then number 2 is ideal gas assumption. You all know by this time, but let me repeat it once again. So, we assume that air which is drawn into the engine cylinder for the CI engines, even for the modern CI engines, it is not only pure air that is drawn into the engine cylinder during intake stroke, rather it is air fuel mixture, because there are multi-port fuel injection system, it is called MPFI. For a multi-port fuel injection system, air fuel is sprayed into the air or incoming air even in the intake manifold or different locations. So, we can say that 90% or 92% or 91% is fresh air and remaining 7% is liquid fuel, or if it is fuel in the vapor form, but still it is not pure air. So, we can still consider the intake air or air which is drawn into the engine cylinder during intake stroke to be an ideal gas. It is still okay, but approximating combustion products or exhaust gases as ideal gases or as an ideal gas, I should say it is not a very important or rather correct assumption. I should say it is a wild assumption rather, because approximating combustion products or combustion gases as ideal gases or as an ideal gas or mixture of ideal gas maybe will reduce calculation or our analysis, but it will ensure some errors in the analysis. So, this is what is very important. But as I said considering air fuel mixture which is drawn into the engine cylinder during intake stroke to be an ideal gas, it is still okay, because 91% or 92% depending upon the requirement is fresh air, while remaining 7% or 8% is fuel. So, it is still okay, but combustion gases are no longer cannot be treated as an ideal gas. So, this is important. Number 3 is, as I said you, constant specific heats, that is constant Cp, Cv, etc. So, try to understand, we had assumed that the combustion process can be mimicked by a constant volume or constant pressure heat addition process. So, if it is mimicked by a constant volume heat addition process, then we use Cv to remain constant throughout the process, while if it is the combustion process is mimicked by a constant pressure heat addition process, then it is assumed that Cp will remain constant throughout the process. But it will not be true in real application, because Cp and Cv is they are function of temperature. So, certainly even if we talk about ideal gas, so Cp and Cv of an ideal gas, these two specific heats are not constant, rather they are function of temperature. Certainly, if we consider the gas to be a calorically perfect gas, which is a special type of ideal gas, we can assume Cp, Cv to be constant, but assuming incoming air or inlet intake air to be an ideal gas and considering the charge to be an ideal gas and mimicking combustion process by a constant volume or constant pressure heat addition process, wherein maintaining Cv and Cv constant is really an approximation, and it will certainly lead to some error. Then number 4 is heat loss. So, all these are so there are two different ways of heat loss. First of all, this is during combustion. We all have studied that when there will be combustion will occur, essentially the temperature and pressure of the working substance or charge will be more, and then certain amount of heat should transfer from the combustion chamber through engine cylinder wall to the coolant. So, this heat transfer will reduce the peak pressure and temperature of the cycle, which in turn will reduce work output. So, I am writing here heat transfer during combustion, and it will reduce peak pressure and temperature, and eventual consequence to this event is reduction in work output, reduction of work output. Similarly, heat loss will be there during expansion or power stroke. So, during expansion also that we know piston will travel from inner dead center or top dead center to the outer dead center or bottom dead center, and while combustion gases are expanding, during the process of expansion certain amount of heat will be transferred from the combustion gases to the surroundings or even to the coolant, because we need to supply coolant continuously, essentially to save several parts of the engine out of excessive heating or from their excessive heating. So, this heat transfer during expansion stroke will also lowers pressure and temperature P and T. So, heat transfer during combustion process will lower peak pressure and temperature, which in turn will reduce the work output, but during expansion process transfer of heat from the combustion gases to the coolant or surrounding will lower pressure and temperature as well, and this will allow this will allow pressure and temperature to become below. So, if I go to the next slide, heat transfer during expansion process will lower the pressure P and temperature T below the ideal isentropic process at the end of power stroke, at the end of power stroke, right. So, you know that isentropic, so the compression process and expansion process, these two processes are approximated with the reversible adiabatic processes. So, that is isentropic processes. So, if we really consider the transfer of heat during expansion stroke, that is transfer of heat from the combustion gases to this coolant or surroundings, this process will allow pressure and temperature to go even less or below the ideal isentropic process at the end of the power stroke. So, this is the case, and if it is the case, eventual consequence of this particular case or will be the reduction in indicated thermal efficiency. Indicated thermal efficiency eta thermal indicated. So, this is the 4, and let us consider about 5, the point 5, that is combustion require combustion process requires finite time, right. So, this means any process needs some non-zero finite time, but if we assume that the combustion process is instantaneous, so it means it is really not possible to transfer heat instantaneously. That means, if we consider the real process wherein combustion will require certain amount of time, as a result heat transfer will not be instantaneous, and if it is not a case, then assumptions of constant volume or constant pressure, these two will not be true, and hence the actual cycle will certainly deviate from the ideal one. Then number 6 is, that is blow down. Blow down requires finite time. So, we know what is blow down. We have studied that when piston is travelling from top dead center to the bottom dead center, before it reaches BDC, that is bottom dead center, exhaust valve is allowed to open. Nowadays everything is electronically controlled, no valve is controlled by cam and follower mechanism. If it is a case, then there certainly with the aid of electronic control unit we can really minimize or reduce the valve timing or time needed for the valve operation. But what will happen, that if valve or exhaust valve is allowed to open before piston reaches at BDC during the end of expansion stroke, so what will happen, certain that means piston did not reach at BDC, we are allowing exhaust valve to open, certain amount of combustion gases will escape from the engine cylinder to the surroundings, and then certain amount of work output will be lost, because if we reduce the gas pressure, so the thrust that will be acting or will be applied on the piston face will be reduced, and as a result certain work output will be lost. So, this is the consequence of this particular event is I can write some work at the later part of expansion is lost. Okay. And if we go to the last point, that is point number 7, that is the valve timing actuation. So, this is again very important common factor which is common for both SI and CI engines. This particular factor is responsible to make a difference between ideal and or air cycle and the real cycle. So, valve timing, you know that as I said now that few minutes back, nowadays no valve is operated using cam and follower mechanism. Instead, everything is controlled by electronically control unit. Now, if we can reduce the timings for the valve operation, certainly we can control the amount of air to be drawn into the engine cylinder. We can also control elimination or reduction of the manual intervention, and also that what we can say that if we can have proper valve timing, as I said you that opening and closing of valve needs some non-zero finite time. So, the delay associated with valve opening and closing will also create some issues with the total amount of exhaust gases that will escape from the engine cylinder and total amount of air to be drawn into the engine cylinder, and hence actual scenario will be certainly different than what is considered in ideal air cycle. So, considering all this, so as I said you the consequence you know very well that from the indicated diagram, if you try to recall, there is a particular period which is known as valve overlapping. That means both valves are open, and what is happening, I mean intake valve will remain, exhaust valve will remain open, and during that time intake valve is allowed to open during intake stroke. So, certain amount of fresh air or fresh charge will allow the residue of the combustion gases to leave as the exhaust valve is remaining open. While doing so, certain amount of fresh charge also will be lost with the exhaust gases, and it will essentially reduce the overall efficiency of the engine. So, if I write the consequence, this is leads to valve overlap and so this part is essentially deviating the real cycle from the ideal one. So, deviation of real cycle from the ideal cycle. So, these are actually the common differences for both the CI and SI engines operation, and these factors, since these factors are common, we can assume that all these factors are responsible to make some differences between real cycle and actual or ideal air cycle. So, if you now go to, as I said you, there are some special features or there are some unique features which are special to CI engine operation, and we shall discuss about those factors only, and these factors are responsible to affect the CI engine performance. So, if we write now unique features or factors which are special to the operation of CI engines. Okay. As such, while I am telling this, it is very important to know all these unique features or factors which are responsible also to affect the engine performance. As I said, that objective of today's class is to discuss about the factors affecting CI engine performance. Let us now try to list down all these factors, and we will see in which capacity all these factors try to reduce or affect the engine performance. So, first one is, if I write, number 1 is non-constant pressure combustion of fuel. So, essentially now we are talking about CI engines. So, we know that in a CI engine, combustion process is mimicked by a constant pressure heat addition process. But in reality it is seen that assumption of constant pressure combustion process, that is, if we assume that combustion process which is mimicked by a constant pressure heat addition process is not always true for the CI engines. Okay. So, this is not always true for the CI engines, right. So, this is maybe that we had seen that this is maybe for actual CI engine cycle, actual CI engine cycle, constant pressure heat addition, constant pressure heat addition is only approximated at lower speed range. Okay. But if the engine operates at higher speed range, then this is not a case. So, that means throughout the range of the speed, if we assume that the combustion process can be well mimicked by a constant pressure heat addition process, then essentially you are trying to invite some error in the analysis. So, this is very important point. This is true, but at higher speed range, this process is approximates more or less process, that is combustion process, approximates more or less a constant volume process. So, this is which is very important too at this point. Okay. So, if you go to discuss about the next point, point number 2, that is dissociation. So, that is dissociation, which is that dissociation means at high temperature that fuel will start dissociating. So, the rise in temperature inside the combustion chamber, particularly for the CI engine, is relatively high as the compression ratio is high. So, since the compression ratio is high, so essentially pressure will be very high at the end of the compression stroke, and at the moment or at the end of the compression stroke, when fuel will be burnt, then again the rise in pressure and temperature will be very high, and at that temperature fuel may be dissociated. So, dissociation will be there. Now, this is a common factor though for both SI and CI engines. So, let me write a few points for this factor, that CI engines or CI engines deal with heterogeneous mixture, and the mixture is lean as well, Okay. So, for this, these two factors, reduces these two factors reduce the gas temperature, and the possibility of dissociation becomes less, right. So, this is one important point. So, though this is a common factor for both SI and CI engines, typically it is this particular aspect is more vulnerable for the CI engines, because CI engines are typically operated at a relatively high temperature, but the question is, rather the most important part is, CI engines deal with heterogeneous mixture of fuel and also with lean mixture. Hence, the gas temperature will be reduced because of these two factors, which in turn will reduce the possibility of dissociation. Okay, let me write the third point. So, the third point is blowdown loss. So, blowdown loss, we know that what is blowdown loss, because few minutes back I said that exhaust valve is allowed to open before piston reaches at BDC during the end of expansion stroke, and it essentially reduces the gas pressure in the combustion chamber. The idea is to remove certain amount of combustion gases before piston again travels back from BDC towards TDC. But in doing so, what is essentially done is the total work output towards the end or later part of the expansion stroke. So, this is very common even for the CI engine. So, let me write this blowdown losses, this is similar for both SI and CI engines, certainly if the engines are 4-stroke cycle engine. Okay, if the engine is 4-stroke cycle engine, but this part is, so this part is significant for 2-stroke cycle, this part is significant for 2-stroke cycle CI engines, because the reason is that this is mainly due to shortened effective power stroke, which is necessary for early release of burnt gas, early release of burnt gas or burnt gases, in order to achieve better scavenging. So, we know the scavenging is a process wherein combustion gases are automatically allowed to leave the combustion chamber by the introduction of intake or fresh charge. So, that is why the power stroke is effectively shortened, and which is essentially for the early release of burn gas or gases to achieve better scavenging. So, this is then last point is pumping loss. So, number 4 is pumping loss. So, let me draw for this particular point. So, if we try to draw the indicator diagram that we have studied in our basic internal combustion engine course. So, this is, so if we try to draw the indicator diagram, so this is the indicator diagram. So, you can understand, so this is called positive work and this is negative work. So, this negative work is essentially blow down work. Now, cycle absorbs energy for or absorbs works during this part of the cycle, and this is called pump work. So, if I write here that this is absorbs work, energy or work, certainly energy in the form of work from the engine, right. We know very well that engine will get power output from the power stroke only, while to operate or to execute 3 other strokes we need to supply power to the engine, right. So, that means this particular work, the cycle absorbs work from the engine to have this particular cycle or process. Now, this is known as pumping loss. So, what will happen, that pumping loss, it is very small for CI engine. So, for 4 stroke cycle CI engines, negative work or pumping loss, exists is very small. Okay. Since there is no throttle in the intake manifold, right. But this is very small, we have written for the 4 stroke cycle SI engine, while this is significant for 2 stroke cycle engines, right. So, we need to have something in real applications, so that though it is very small for the 4 stroke cycle SI engine, but this should be reduced essentially to improve the engine efficiency. Okay. So, now the last part that I would like to discuss is air consumption. In a CI engine, right. So, we all know that so for the CI engines there is no throttle valve, but for the SI engines we had seen there is a throttle valve. Essentially what is done by controlling the throttle position, that if you try to recall the performance maps, then we had seen that the upper part of the map corresponds to full throttle power output or operating characteristic, while the lower part of the map corresponds to part load operating characteristics. So, but in case of a CI engine there is no throttle valve. So, essentially what is done, the fuel is controlled to control the work output. So, let me write here just 2-3 lines I will write. So, no throttle valve to control the airflow, right, that is important. Power output is controlled by the fuel amount, right. So, that means for a given engine speed, though this is true, but if engine speed increases, certainly the amount of air to be drawn into the engine cylinder will be more, then frictional loss also will be more. So, let me make you understand that though there is no throttle valve to control the amount of air to be drawn into the engine cylinder, essentially power output is controlled by the mass flow rate of fuel. But as this is true for a constant speed, but as the engine speed increases, the amount of air to be drawn into the engine cylinder will increase, and also the frictional losses will increase. So, all these things are not taken into account in the ideal cycles, and also you know that if we have even given inlet and exhaust valve timing, then we really can control the amount of air to be drawn into the engine cylinder. Now, the question is this, or controlling the valve timing, rather intake and exhaust valve timing, we really cannot optimize the engine performance at higher and lower speed. So, what is important to be mentioned here is that the volumetric efficiency is again coming, or seems to be an important factor for the SI engine performance. So, the amount of air which should be drawn into the engine cylinder, though it is not controlled by the throttle valve, but plays an important role for the CI engine performance, and this is not only the amount of trapped air inside the engine cylinder, but the proper utilization of the trapped air should be ensured to have better engine performance. So, to summarize our today's discussion, we have recapitulated the basic differences between air cycle and real engine cycles for both CI and SI engines. Thereafter, we have identified a few unique features which are solely responsible for the CI engine operation, rather those unique features differentiate CI engine, actual CI engine cycle and from the air standard cycle. And then listing down all these important unique features, we have explained each and every points, and finally you had seen that air consumption in a CI engine is also very important, which in turn indicates that volumetric efficiency is also very important for the CI engine performance. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.